Good day, colleagues. My name is Yuri Kagramanov and I'm a user of reaction design products. Today I'm going to present a short user review and describe the way I calculate objectives by tools of Ansys Fluent, Energico and CHEMKIN-Pro. CHEMKIN is a software package whose purpose is to facilitate the formation, solution and interpretation of problems involving elementary gas phase chemical kinetics. It provides a flexible and powerful tool for incorporating complex chemical kinetics into simulations of fluid dynamics. The package consists of two major software components: an interpreter and the gas phase subroutine library. The interpreter is a program that reads a symbolic description of an elementary user-specified chemical reaction mechanism. One output for the interpreter is a data file that forms a link to the gas phase subroutine library. This library is a collection of about 100 highly modular Fortran subroutines that may be called to return information on equations of state, thermodynamic properties and chemical production rates. CHEMKIN includes capabilities for treating multi-fluid plasma systems that are not on thermal equilibrium. These new capabilities allow researchers to describe chemistry systems that are characterized by more than one temperature, in which reactions may depend on temperatures associated with different species. Reactions may be driven by collisions with electrons, ions, or charged neutral species. These new features have been implemented in such a way as to require little or no changes to CHEMKIN implementations for systems in thermal equilibrium, where all species share the same gas temperature. In the late 1970s, Jim Miller and Robert Key began to collaborate on modeling combustion, chemical kinetics and flame structure at Sandia National Laboratories in Livermore, California. Even as a freshly graduated PhD, Jim brought an extraordinary deep understanding of fluid mechanics, thermodynamics and chemistry together, with a keen vision how combustion modeling should proceed and what it could accomplish in the following decades. And that theoretical foundation and vision set the course for much of what was included in CHEMKIN. Once the basic CHEMKIN philosophy and software were established in 1980, with a framework into which new models could be integrated. Thus, it became possible to expand the integrated modeling tools efficiently to meet the needs of increasingly challenging applications. Over the years, more than 20 individuals have contributed to aspects of CHEMKIN. Major contributors include Fram Ripley and Alan Mix from Reaction Design, Leach Larson and Andy Lutz from Sandia National Laboratories. Active international collaborations played a critical role in developing modeling capabilities. The frequent interactions with Jürgen Warnatz, University of Heidelberg, and his group over 2 decades have had a substantial influence on the course of CHEMKIN modeling philosophy. Collaborations with Graham Dixon Lewis, University of Leeds, and Jürgen Warnatz led directly to the molecular transport formulations and CHEMKIN implementations. The original state reactor software grew out of collaborations with Peter Glaborg, Technical University of Denmark, who has contributed collaboration with Jim Miller on nitrogen cycle chemistry, understanding of fluid mechanical similarity in various combustion situations, have benefited greatly from long-standing interaction with Tadao Takena, Majo University in Japan. CHEMKIN-Pro can solve a big range of objectives. Now it can be used in different fields of industry, Combustion family reactors could be interesting for furnace and boiler flare systems and internal combustion engines manufacturers. Microelectronics family of reactors has methods for CFD, both stationary and rotating processes modeling. Plasma reactors, closed, perfect stirred and plug flow simulations. Catalytical and heterogeneous reactions can be solved in chemistry family of reactors, like planar and cylindrical, shear flow and honeycomb reactors. All of these elements can be joined together by means of miscellaneous library that include inlets, outlets, gas flow splitters, and external source of initialization. While CHEMKIN-Pro carries out simulations in its own shell, Energico can provide this software a connection with external CFD processors like Ansys Fluent. Energico asks for several input parameters that used to be pointed during CFD data file export. These parameters are static pressure, static temperature, density, velocities, turbulent kinetic energy, turbulent dissipation rate, mass fractions of all CFD species. The experimental apparatus is a co-flow burner with mass flow meters to supply fuel and oxidizer, and an emission analyzer Testo 300M as shown in figure. The fuel was supplied through a mixer filled with glass beads for homogeneous mixing, and used chemically pure methane mixed with ammonia. The volume ratio of ammonia in the fuel was changing. The mixed fuel was supplied at a constant flow rate of 400 cubic centimeters per minute through the central nozzle with an outlet diameter of 1.27 centimeters and an inner diameter of 0.43 centimeters. The initial jet velocity of the gaseous fuel was 47 centimeters per second. Chemically pure oxygen and nitrogen were supplied at a constant flow rate of 15,000 cubic centimeters per minute, mixed in various proportions of oxygen and nitrogen, with a co-flow with inner diameter of 15.6 centimeters. The oxidizers were supplied through the glass beads and a honeycomb for flow uniformity. The initial velocity of the co-flow oxidizer was 1.3 centimeters per second, and the volume ratio of oxygen in the oxidizer was changing. The coaxial flow was contained in a Pyrex tube with a height of 60 centimeters to block the disturbance from the environment. A circular cone-shaped metal structure that collects exhaust was installed on the top, and NOx was measured by placing a probe for gas measurement at an outlet 90 centimeters away from center of the nozzle. NOx was determined by summing nitrogen monoxide and nitrogen dioxide with the proportion of NO in NOx by an approximately 95%. The maximum measurement error under steady-state operation was plus minus 2 ppm. CHEMKIN results give overstated information no more than 5%. Add ammonia volume fraction equal to 5%. Difference between experiment and simulation rises from 0 to 5% for CHEMKIN solution and from 0 to 13% for Fluent solution. After 10% of ammonia volume fraction overstate decreases down to 2% for CHEMKIN and to 8% for Fluent. Oxygen change didn't make any significant effect on CHEMKIN solution accuracy, and is still better than
Fluent reduced mechanism.
Integrated gasification combined cycle, shortly EGCC, is considered one of the most important systems for future coal utilization technology in power generation systems, and is being promoted throughout the world. In Japan, the government and electric power companies undertook experimental research at a 200 tons per day pilot plant project from 1986 to 1996. The Central Research Institute of Electric Power Industry developed an air-blown pressurized two-stage entry-flow coal gasifier, a hot-dry synthetic gas cleanup system, and 150 megawatt gas turbine combustor technologies for low BTU fuel. Of late, the government and electric power companies are promoting a demonstration EGCC project. Other developments concerning an EGCC system and gas turbine combustor using the oxygen-blown gasifier coal fuel include the Cool Water Coal Gasification Project, the flagship demonstration plant of EGCC, the Shell process in Buchanan as the first commercial plant, which started test operation in 1994, with commercial operation from 1998. The Wabash River coal gasification repowering plant in the United States, in operation since 1995. The Texaco process of the Tampa Power Station, in commercial operation since 1996. A heat coal gasification process for the purpose of hydrogen production, which was developed in Japan, and the integrated coal gasification fuel cell combined cycle pilot plant, which consists of gasifier fuel cell generating unit and gas turbines, in a test operation from 2002 from Electric Power Development Company in Japan. Furthermore, the diversification of fuels used for the electric power industry, such as biomass, poor quality coal and residual oil, are also the most significant issues for gas turbine development in EGCC. The development of biomass-fueled gasification received considerable attention in the United States in the early 1980s, and the prospects for commercialization technology appear considerably improved at present. Figure shows an outline of the combustor and the tested burner. The combustor consists of a cylinder-style combustion chamber with an inner diameter of 90 mm and length in 1000 mm, and a primary air swirler and fuel injection nozzle. The combustion chamber is lined with heat insulating material, and the casing of cooled with water. There are 4 sections for secondary air on the side walls of the combustion chamber along the direction of flow, to simulate an actual air inlet distribution of the gas turbine combustor. In order to investigate the effect of the two-stage combustion on the fuel NOx and thermal NOx reduction, secondary air inlets at a distance from each of the fuel injection nozzles of 3 chamber diameters are used. The diameter of the secondary air inlets at the entry of the combustor is 13 mm, and altogether 12 inlets are positioned on the perimeter on one cross section. The tested burner consists of a fuel injection nozzle and a primary air swirler. There are 12 injection inlets with a diameter of 1.5 mm on the fuel injection nozzle, with an injection angle of 90 degrees. The primary air swirler has an inner diameter of 24 mm and outer diameter of 36.4 mm and 12 vanes with a swirl angle of 45 degrees. The combustor exit gas temperature was set to 1773 kelvins.
and the fuel injection velocity was set at a constant value of 77 meters per second. The cross-sectional flow velocity of total air was 0.53 meters per second at the temperature of 273 kelvins, basis in case. CHEMKIN accuracy was in range from 5 to 20% versus from 15 to 45% of Fluent. The maximum disagreement between experiment and simulation results was detected at equivalent ratio equal to 1. And now I'd like to end my presentation and to move on to my tutorial. Well, here's our working folder here. In this series of videos we won't consider geometry and mesh generation. We'll take a prearranged mesh file that you'll be able to download from the link below. Next, we'll consider how non-premixed combustion model can be set up in Ansys Fluent, what chemical libraries and where it is possible to take it from. And finally, we will carry out data transfer from Fluent into Energico and from Energico into CHEMKIN-Pro. This is a GREEMESH format chemical library which contains kinetic data for more than 400 reactions, including pre-exponential factors, temperature power indexes and energy activations. And you can read all of this data with an obvious text editor. The next file is thermodynamic data for current components. Both of these files were taken from the site of the combustion laboratory of the University of California, Berkeley. You can find this page quickly by clicking the link below. And now let's start our Ansys R2 Fluent in 3-dimension mode and read current mesh file. I'll see you soon in the next part. Now we can see our mesh in Fluent preprocessor. Geometry and boundary conditions were taken from these two useful articles. Check the links below. I strongly recommend you to read these both studies. There were plenty of important information about nitrogen monoxide formation and ways of its reduction in gas turbines for coal-fired integrated gasification cycles. Let's move back to Fluent and quickly set up all the models. In this case we will switch on the K-epsilon RNG model with swirl-dominated flow and enhanced wall treatment functions. Next we will set up a non-premixed combustion model with a non-adiabatic flame. Import GREEMESH kinetic library and thermodynamic data files from the working folder. In boundaries, we will set up 90% mole fraction of methane and 10% of ammonia. And be careful with that mole and mass fraction mode, and set up temperatures that fuel and oxidizer have on inlet. In my case it is 503 kelvins. Let's calculate flamelets and save it to our working folder. These results will let Fluent to calculate the PDF table. The process will take some time. You can also display PDF table in the form of diagram. Oh yeah, let's write it to file. We've done with models setting for a while, and let's check the materials. You can see two types of mixtures, PDF mixture and flamelet mixture. As you can see, PDF mixture is reduced. It contains only about 20 reactions, while flamelet mixture is a build-up of more than 50 species. PDF method do not calculate all the green mechanism reactions, but only the main part of it. In boundaries, you can see two types of inlets, for air and for fuel, and here in graphic window represented an air inlet configuration. You can see that several perpendicular sections along the chamber and one swirled inlet in the bottom. Here is a fuel inlet configuration. Let's set up mass flows, temperatures and composition for both inlets. We will put mean fraction parameter in species, 1 for fuel and 0 for air. Now we are ready to move on. See you next part. We're back now and we're ready to simulate. But before we start to run calculation, let us set up some monitors to check the most desirable output parameters, which are temperature and nitrogen monoxide mole fractions, both on outlet. Finally, let's initialize and run simulation. And don't forget to back your case and data up. And maybe counters of the same values would be useful too. Here we can check our changing results and unexpected good convergences trend in residuals monitors. Here you can see that our temperature is not changing and it is approximately equal to 1000 kelvins. And the same thing is with NOx.
We can find proper values in Fluent parameter bar. 70 ppm at 1019 kelvins we've got. Remember these values, we'll use them in the future.
It took only 120 iterations to converge this solution. Really nice. The same case with 100% of methane took at least 500 iterations as far as I remember.
Now let's write our case in data one more time and export the same to the special Energico format called CGNS. To do this we need to switch on the cell-centered mode and to select number of parameters like static pressure, density, velocities, temperature and mass fractions. All of them. And now we reached the Energico preprocessor. So next part, before we start our exploring of Energico, let's get back to Fluent and check will there be any changes in results if we switch on radiation model. Obvious discrete ordinates by default. As you can see, things have changed.
There is no more such a perfect convergence as it was at previous time, but still, there is a good trend. So I decided to stop somewhere closer to 1000 iterations. And maybe I was right, cause temperature tended to stop its change. Parameter bar shows that temperature fell on 100 kelvins while NOx didn't change significantly. Let's overwrite our case and data files and also CGNS file. Finally, here we are, Energico. Surrender with the warmth and tender. Well, first thing we need to do is to find our working folder. Pretty tough deal sometimes. Next, we need our CGNS file and remake kinetic data in CKS format. That could be found in samples of CHEMKIN in diffusion flame in a folder. Then select Control Volumes. And now the most challenging thing, I guess, are species and CFD symbols connection. Well, solid nerves to all of you guys. Now we need to set Energico units, the same as it were in our Fluent case, manually. And don't forget about pressure. In our case it was ambient and absolute. Fill the boundary table, let it know everything about your case, and it will open the gates to equivalent reactor network tools. There you will find our combustion zones, column, algorithm buttons, and even manual tools for its generation. We'll use one of Energico's algorithms to build these combustion zones. It is based on fuel and oxidizer species mass fractions. Now when zones are built, we need to assign reactor types for each zone. According to Energico manuals, several manipulations used to be done. Now we are ready to switch on CHEMKIN-Pro and to end it all as quick as it possible. See you next part. Let's get back to CHEMKIN. Here you can see this large diagram window where we can put different elements from the model bar. But we won't. Energico did all this stuff. The only thing we need to do is to push the button, run calculation, and step back. It's really quick. Let's watch the results. I will export it to Excel. As far as I remember, Fluent calculated NOx fraction equal to 70 ppm, and now CHEMKIN says that it is 171 ppm, and if I am not mistaken, the truth is somewhere near 170 ppm. Now it's all over. Thank you very much for your attention. Enjoy yourself and goodbye.